this is a second lecture, module 4. So we are this is the lecture number 18. So now here what I planned is to find out a transformation matrix for a elasticity matrix or the constitutive matrix. So this is a very special case before I start this. So in general 3D rotation are not additive, it is non-commutative. So essentially what it means, that means if you rotate a coordinate system, first this and then this and then this again this, so it is not commutative. So so 3D rotations we are not discussing here. So in general what we are discussing here, it is rotation about an axis or rotation of a plane. So rotation about an axis. So for instance, this is a x and y. So it may be important to point out here that rotation about an axis means that the rotation matrix, or the three-dimensional rotation can be rotation about an axis or rotation of a plane. So for instance, we have seen in the last modules or last class itself that rotation matrix, if I rotate a about an axis, the transformation matrix is 3 cross 3 matrix. So here first what is our objective today is to first to derive the stress strain transformation, which all of you know from your basic theory of elasticity, basic strength of material or the solid mechanics course, but we will just briefly go through it. And finally our objective is, since we transform stress, we transform strain, so what will be the transformation for the constitutive matrix? Now here we also know that the constitutive matrix is a fourth order tensor, and this fourth order tensor how it transforms through the ij kl. If you remember this formula, which is q I p q I q and q I r and q I s and c p p q r s. But this is a this formula, it is impossible to write it in a matrix notation. So sometimes it is very handy, and we will be having several engineering application of that what we will study today. So essentially if I rotate about an axis, what will be theCijkl or in the prime coordinate system. So that is our objective. So now we can essentially transfer these quantities and equate with that the procedure we will derive today. So and then we have to find out the sequence of rotation, and then we have to do this for all components ofCijkl. Instead of that, if I have a simple rotation about an axis, then what should be my transformed coordinate matrix? That is my objective here. So let us start with 2D transformation. So we know 2D transformation from +2 level or plus 10th level itself. So 2D transformation is, if I rotate this x y axis to x prime y prime, we can write x prime equals to x cos theta y sin theta, and y prime is minus x cos theta y sin theta. So essentially q is cos theta sin theta minus sin theta cos theta, and this can be sometimes represented as L1 M1 L2 M2. So there are various representation. C1 Cs also sometimes it is written in this form also in the book or any literature you will see this. So Cs minus S C, in this form also it is possible to write. So here we are denoting L1 M1 L2 M2. So now here naturally this inverse transformation is also possible, which is x y equals to x prime cos theta. So, which is inverse transformation is q transpose, because q is an orthogonal matrix. So, q transpose is q inverse and det of q is plus 1. So, this is a rotation matrix. So, we know the properties of the rotation matrix. So, now, if we take the derivative, so partial with respect to the axis, so del x by del x prime, so which is essentially cos theta minus sin theta and cos theta. So, this we know, this will use it. So, now let us see if we, so essentially what we have learned here, we can rotate the coordinate system and we know the coordinate system. And one important thing maybe I should point out here, that q can be written in 3D format also. So, which is essentially c s minus s c and then 0 0 0 0 1. So, it represents a rotation about a z axis. So, a rotation of xy plane. So, essentially it is a one parameter parameterization of the rotation matrix. So, it is better to know here that 3D rotation cannot be parameterized by one parameter. There are several ways to do it. For instance, quaternions is there, Euler angles are there. Those who study rigid body dynamics, they may know it. We are not talking about those rotations. We are rotations, our rotations are about an axis or rotation of a plane. So, that is our basic thing. But these formulas with slight modification can be applied to for general rotation also. So, that obviously we will not discuss in this course, and we do not have the applications for this course. So, let us see how similar to the this thing coordinate transformation, we can transform a vector also, which is a displacement vector. So, u prime and v prime is related as u cos theta v sin theta and minus u sin theta v cos theta. So, in xy axis it will look like u v vector and u prime v prime. So, in a 3D case also it is same, in the 3D case it will be u v w. So, now our main objective is to derive strains. So, which we know from our strength of material concept, and that is why I started with the 2D problem. So, let us see how we can transform the strains. So, now essentially strains are here. It should be noticed here that I am using here the gamma xy, that shear strain. So, which is essentially 2 of epsilon xi. xy. So, we keep it in this format. So, here we will have the some benefit of doing that. Now, q is this. So, essentially strains will be transferred here. So, now in a tensorial notation we know this how to transfer strains. So, if I have a rotation matrix, then I know from our tensorial this thing in the previous class itself, we know that epsilon prime is essentially q epsilon q transpose. So, here these epsilons are second order tensor. So, second order tensor, it should be remembered here. So, and this is a orthogonal matrix. So, q is similar to this, or also a second order tensor. So, it is in a matrix format. So, this gives me a transformed second order tensor, which is a these things. But we wanted to have this in a vector format, or specifically this can be modified in a void notation also. So, the void notation also we know this is epsilon x is essentially your epsilon 1, epsilon y is epsilon 2 and so on. So, we know this. So, from our earlier lectures. So, now how to essentially how to find out this T epsilon or the transformation matrix for the strains. So, that is my main objective. So T epsilon, you see that this is a matrix. We are not talking about tensors here anything. So we are talking about a matrix. So essentially this will be a 3 cross 3 matrix, because this is a 3 cross 1 vector and this is a 3 cross 1 vector. So this T dimension of T epsilon will be a 3 cross 3 matrix, and which we can arrive from our strength of material knowledge itself. So let us see how we can arrive this. So essentially strain components are del in prime coordinate system, it is del u prime del x prime and so on, and non-prime coordinate system del u by del x and so on. So if I write what is the relation between these two, so epsilon x prime is essentially this. This probably you have, this is very familiar expression. Those who have studied more circle in strength of material or coordinate transformation or strain transformation, so you know this formula. And how to derive this formula? You derive essentially epsilon x prime is essentially del u prime del x prime. So this I can write it simply del u prime by del x into del x by del x prime, and then del u prime by del x del y into del y by del y by del x prime. So you know this from the coordinate transformation that we have seen. So and then del u prime also you know, because if we substitute del x of u prime, what we know is u cos theta plus u sin theta v sin theta, and then del x by del x prime is essentially your cos theta. And then similarly for del u prime, again we substitute this del y of u prime u cos theta plus v sin theta into del y by del x prime, which is sin theta. So like this we can arrive this cos square u cos square theta. So del u by del x will be the first term cos square theta, and then del from here it will come the del y del v del y by sin square theta, where it will come here this quantity, and then cos theta sin theta, that is del v by del x plus del u by del y cos theta sin theta. So this will be 2 times of this. So this will be if I write it in a engineering strain component, it looks like this. So essentially we can simply write here del u del x cos square theta plus first I write this quantity, so del v by del y sin square theta, and then plus del v by del y plus del u del v by del x del u by del y. So this is into sin theta cos theta. Sin theta cos theta. Now you see carefully, this is del u by del y and del v by del x is essentially gamma xy, which is a shear strain, and then del u by del x is epsilon xx, and then del v by del y is epsilon yy. And similarly for epsilon y prime we also can derive, and this equation also you know it from our strength of material knowledge. So this also we can derive for the shear strain. So if you remember these things, so we can express it from a in a matrix format, and probably we have studied this earlier also. So let us see how it looks like. So this is the formula, and then if we substitute L1 equals to cos theta, M1 equals to sin theta, L2 equals to minus sin theta, M2 equals to cos theta, then we get this T sigma T epsilon. So, T epsilon we get it from the these formulas. So, this is applicable for 3D also. So, the in a similar way, if we can express the strain quantities in a rotation about an axis or rotation of a plane, then we can also derive T epsilon or the transformation matrix for strain for 3D case. So, this is we know it from the our basic knowledge. Now, from our strength of material knowledge. Now, with this T epsilon we get the strength transformation matrix. So, similarly stress transformation, the stress transformation also we can go with the similar procedure, and if there is a rotation about a axis, it can be proved by T sigma is essentially T epsilon inverse transpose, and T sigma transpose essentially if you take the transpose, then T epsilon inverse. So, this can be proved very easy way also. There are two ways. If you know the virtual displacement or virtual walk principle, that will also give you the same result. Otherwise, you can use the invariance of the strain energy function, which will you know the strain energy function is essentially strain energy function essentially is half of epsilon into C into epsilon transpose C into epsilon. So, now if I write half of sigma or the epsilon transpose, in place of this I write sigma, so I can write it is half of sigma transpose E epsilon. So, if you do this for a transform coordinate, since we know u and u prime are same. So, because it is an invariance relation, strain energy is invariant. So, now this we can achieve for the and we know the epsilon prime we know. So, we can achieve the these relations for the rotation about an axis. So, now with this in mind, we can approach for a what will be the constitutive matrix. If I now what we have seen? We have seen how to transform a coordinate, how to transform a vector, general vector, for instance displacement, strain, displacements, and then we transform a second order quantity essentially written in a void format, that is strain and stresses. So, which will have the specific transformation matrix, essentially that is not a rotation matrix. So, basic purpose is T sigma and T epsilon are not rotation matrices. So, but it contains the component of the rotation matrix. So, now in a so finally the transformation matrix for the for constitutive matrix is as follows. So, in a XY system we know what is the Hooke's law. In a XY x prime y prime system also we know what is the Hooke's law. Now, if we write sigma prime is essentially T sigma into sigma, so stress transformation, then we can substitute T sigma, the previous relation that we have discussed, T epsilon my inverse transpose, we can substitute this, and then with this T epsilon inverse transpose, I can again write it in T epsilon transpose sigma prime. So, because I just shifted, I just multiplied with the T epsilon transpose here. Here I multiplied with the T epsilon transpose, and here I multiplied T epsilon transpose. So, which is A inverse or TT inverse kind of thing. So, which is identity matrix. So, I just flipped the side. So, sigma is essentially T epsilon transpose sigma prime. So, now this sigma prime, again I can write C prime epsilon prime from this relation. So, this C prime epsilon prime, again epsilon prime I can write it T epsilon into epsilon. So, I transfer it to the non-prime coordinate system. Now, if you look carefully, this quantity which is in the second braces, this is actually the C, because sigma is essentially C into epsilon. So, this is essentially C into epsilon. So, I can write C is equals to this, and then again if I do inverse, I multiply inverse and then transpose. So, I get C prime is essentially T epsilon C T prime T epsilon transpose. So, this is a general formula for transformation of constitutive matrix, where again I am pointing out that these formulas are actually valid for the rotation about an axis. So, in general this is not true for a 3D rotation. So, now what exactly it will be different is this. We may not able to use this formula for in general 3D rotation. So, there we have to have a different formula which may not be same as this. So, now we have achieved the rotation about an axis or rotation of a plane where the constitutive matrix will transform, and then we can extend it for the 3D case. The 3D case is very simple. You just have 3 coordinate system where L, M, N are the unit vectors, and then or the direction components of the direction cosines. So, you write x, y, z in this form, and then you can construct the rotation matrix, which is L1, L2, L3, M1, M2, M3 and N1, N2, N3. So, similarly we can transform the vectors. Vector is L1, L2, L3, M1, M2, M3, N1, N2, N3. So, the vectors also we transform in a similar manner. So, here now in a 3D case there will be 6 cross 1 strain vector in a void notation. So, again I am using it here, I am using it the shear strain components. So, now again this quantity is in a prime coordinate system. So, this can be the 3D rotation 3D matrix for the strains transformation. So, it is essentially T epsilon and this is the non-prime quantity. Remember here that in the probably in a 2D case we have seen the rotation matrix in cos theta, sin theta, minus sin theta, cos theta. So, in this form, but in a 3D case it may be like this: cos theta 0 sin theta, and then 0 1 0 sin theta. So, minus sin theta and 0 cos theta. So, in this format it is there. So, this matrix is in this format. Essentially the this Q matrix is one parameter family. So, that is a rotation about an axis and rotation about a or rotation of a plane. So, in case of a finite rotation or 3D rotation means where it is non-commutative, that one parameter is not possible. So, essentially it is a 2D rotation, it is not a 3D rotation, but rotation matrix or the Q is written in terms of 3 cross 3 matrix. So, it is about an axis which is which does not rotate, and which so it is about a plane. So why I am doing this? Because we will be using mostly composite materials. So where we will see the use of these matrices very often, and it has a a very large amount of engineering application. So now the constitutive matrix can be written in the same form. The constitutive matrix here will be in the same form. So this T epsilon is essentially this. So now for a 3D case, this matrices has to be multiplied with the proper non-prime C and to get the prime C. So now this is why we have learned this essentially is to because we will be essentially sometimes we will be using probably I discussed it earlier why we have seen. So let us give through a 2D example where the coordinate axis is like this. So essentially say it is x1 and x2. So x2. So it can be 3D material also. So I am giving you the example of 2D material. Now this is my coordinate axis, and now here it is made of an anisotropic material. But what happens, the anisotropy or the for instance it is a carbon fiber or glass fiber material where the fiber directions are in these directions. So these are my fiber directions. Now what is available essentially is the material parameter or the material parameter along this material parameter along this. What is available essentially is material parameter along these axes. So which is say x1 prime, x2 prime. So material parameter along these axes. So essentially what we will have the C11. So since it's a 2D material, so C11 prime, C12 prime, C12 prime, and C22 prime and C66 prime. So if I take an orthotropic material, so this is my 2D constitutive equation. So it can be represented in terms of E1, E2 and E3 prime, E1, E2 and nu1 to this quantities that is engineering constants, Young's modulus along direction 1 prime, Young's modulus along direction 2 prime. These are also possible. So now this is my constitutive matrix along the fiber direction. This is available. But when we solve through finite element or any this structure when will be solved, we will be evaluating the elemental stiffness matrix, say K E. So which is elemental stiffness matrix. Those who have studied finite element, the elemental stiffness matrix need to be evaluated over the element domain, which is essentially B transpose C B. So here over the integration over the element. So this is C prime. So now you see this this matrix is essentially need to be evaluated. We need C here. So here to solve for C, you this integral is along this x1 x2 coordinate system, x1 x2 coordinate system. So we need this C to be transformed in these coordinate system. That means this C prime need to be transformed in non-prime coordinate system, and to do that, actually if we know the rotation, that is the how these fibers are oriented along x1 x2 plane, so which is essentially say angle theta. So I can define q theta that is the rotation matrix along this, and this can be written in terms of cos theta sin theta minus sin theta cos theta. So, for 2D case. So, now this can be essentially we need to transform this C. So, C will be essentially again T epsilon and then C prime, here it is C prime and then T epsilon transpose. So, now T epsilon again we will find out from the formula that we have derived earlier for 2D case. So, we know these vectors very easily. So, L1 square M1 square and so on, which we have derived here. So, this is very useful to solve this, and we need to transform the material property to the structural axis. So, this is why it is important. So, this C is along the x1 x2, and you will see if you do it on your own with MATLAB or any other software, if you do these multiplications. So, this is an orthotropic material where the 4 independent constants are there, but if you this C may not be look like this form, that means these elements of this matrix may not be 0, that is C here this C may be in general C11, C12, C16, C12, C22, C26, C16, but C26 and C66. This will be symmetric because this is a symmetric transformation. So, now this C will look like this. So, that means that you see that the coupling coefficients which were along x1 x2 plane will be it was 0 1/6 coupling coefficient. So, this is essentially it is a shear strain with the normal strain coupling coefficient. So, this quantity which was 0 earlier in the transform coordinate system, that is x1 x0 or the structural coordinate system or the body coordinate system, which is not 0. So, which is natural if you have an inclined sheet and you are pulling in a different direction. So, it will offer some coupling between the shear and the normal stress. So, this is evidence from this transformation here. So, essentially this is important because we may not have always the material orientation and the structural orientation is same. So, if it is not same, we need to transform the elasticity matrix to the structural coordinate system, and to do that essentially we need to follow this formula. So, this is the basic objective for this lecture. So, I stop today here, and then we will meet you in the next class. Thank you.